Okay. Let's go ahead and get started. I guess there probably aren't, maybe we should have said logistical things, but homework's due Monday, right? Is that right? So that's probably the only logistical thing. Solutions are out. I don't remember if I said that on Tuesday, but they're on Piazza for homework 1, not for homework 2. Yeah, I think that's everything logistically. So let's go ahead and jump back into the proof of Margulis-Gabber-Galil. So what were we doing last time? Well, I have up the last slide on the board, but this is probably meaningless to you at this point. So I'm going to rewrite stuff. No worries about this. So what we were doing last time, basically we were proving that this construction by Margulis of an infinite family of graphs was in fact a strongly explicit family of spectral expanders, meaning that their spectral expansion kind of as n goes to infinity is bounded away from the regularity parameter by a constant. So last time, essentially what we did is we kind of unrolled the Rayleigh quotient, and then we showed that kind of we were stuck, and then we used Fourier analysis to show kind of an equivalent version of the theorem that we'll focus on proving today. And now let me actually write all of this to remind you of where we are. And then we'll actually just jump into kind of proving the Fourier analytic version of the theorem, which won't actually use any Fourier analysis at all. We just needed it to get to the theorem statement. So let me maybe remind you of a few things. So first of all, what are the Margulis graphs? Again, let's maybe go over the definition one more time so we remember what we're actually proving something about. So this is a family of graphs indexed by the natural numbers. Switch to red or black. Where Gn is a graph on z mod n squared, z mod n cross z mod n. And remember that the edges are defined by certain affine shifts. So in particular, I need to define some operators first. So let's let T1, I think, is equal to 1, 2, 0, 1. T2 is equal to its transpose, 1, 0, 2, 1. And then E1 and E2 will just be the standard basis vectors. So E1 is equal to 1, 0. E2 is equal to 0, 1. And then how do we define the edges? Well, the edges are basically just kind of the affine transformations given by these, right? So for all maybe vertices in Zn squared, V is adjacent to what? Well, let's see if I can get it correct this time. V is adjacent to T1V, T2V, T1V plus E1, T2V plus E2, and then the inverse transformations, which are T1 inverse V, T2 inverse V, T1 inverse of V minus E1, and T2 inverse of V minus E2. So this is an 8 regular graph. You'll recall from last time it had self loops and parallel edges, but I claim that we don't really care about this. You can basically ignore them, and we'll just kind of use this definition to work with the expansion. And what was the main theorem we were trying to prove? Main theorem, Margulis-Gabber-Galil. So really some non-quantitative version was proved by Margulis first, and then Gabber and Galil gave this simpler proof of a quantitative bound on the eigenvalues that we're actually finishing up today. So the proof was that, kind of abusing notation a little bit, this is kind of the unnormalized eigenvalue. The second largest eigenvalue in absolute value of the unnormalized adjacency matrix, they prove is less than or equal to 5 root 2, which is strictly less than 8. So they prove that this is an expanding family of graphs. And we won't quite prove this today. We'll actually prove something like 7.3, I think, which is still less than 8. So it's still good enough to prove that this is like a good family of expander graphs. But it's not quite the bound that Gabber and Galil got. The analysis is a little simpler. I don't know why. Is like a bunch of stuff showing on the screen on the slide below for you? Very weird. Does not show on my iPad. Let me switch documents. Let's maybe just go over to this document. Okay, okay, whatever. Technical issues. Not sure why that happened. Let me rewrite the theorem we're trying to prove. Lambda gn is less than or equal to 5 root 2. I said actually we're going to prove 7.3. So this is the main theorem. I want to kind of review what was our direction last time towards proving this. Where did we start and where did we end up before kind of jumping into finishing the proof? So you'll recall that kind of we started with like step 0, which was basically to say kind of our goal is to upper bound the Rayleigh quotient. So what we want to do is upper bound, it's sufficient to upper bound the absolute value of the Rayleigh quotient. Abs value of Rayleigh quotients for functions orthogonal to the all ones vector. And we spent a little bit of time kind of expanding out the Rayleigh quotient in terms of the definition of the edges of the Margulis graphs to get some kind of explicit form of this inequality that we needed to prove. So in particular, kind of what did we want to show? Well, at the end of step 0, we showed that kind of it was enough to prove the following inequality. We wanted to prove that the absolute value over the sum of vertices in Zn squared of f of z times f of t1z plus f of t2z plus f of t1z plus e1 plus f of t2z plus e2. We wanted to prove that this was less than or equal to, so I'm just going to stick with 5 root 2 for now. We'll change to 7.3 at the end. Actually, this should be, we divided by 2 here, so this should be 5 over root 2 times the sum of f of z squared, again, over Zn squared. So this was just from rolling out the definition of the Rayleigh quotient. We got to this kind of equivalent version. And then kind of without other techniques, we were a little bit stuck. We couldn't use our standard method of applying Cauchy-Schwarz because kind of if it turned out that these f of z and f t1z, et cetera, were correlated, the bound you would end up getting is 4 times the sum of f of z squared. But that gives you a bound of 8 on the eigenvalues, and that's a trivial bound, right? We know all of the eigenvalues are between 8 and -8 because it's an 8 regular graph. So somehow we had to beat Cauchy-Schwarz. We had to show that these terms are not perfectly correlated, and therefore that you can get a better bound than Cauchy-Schwarz. And to do this, we kind of reduced, so we kind of got halfway through doing this last class. And what we did was we used Fourier analysis to reduce to a different theorem that kind of had explicit phases on the cross terms that are going to help us decorrelate. So in particular, what did we do last class? Kind of via Fourier analysis, we proved that it's sufficient to prove the following result. So sufficient to show following. And I'll just state this, I guess, as a theorem. For all functions g mapping from the group Zn squared to, actually, I want to write this black. All g mapping from Zn squared to, I guess, the reals greater than or equal to 0, such that, so before we had that, sorry, I guess step 0, I should have said this is for f orthogonal to 1. We only want this to be true if f is orthogonal to 1. It won't be true otherwise. Such that g00 is equal to 0. So why this constraint? Just as a reminder, this is, so g here, what is g actually? Well, it was the absolute value of the Fourier coefficients of f. You don't need to know this. Today's class will be self-contained. So if that at the moment doesn't mean anything to you, it's totally fine. We won't need to use that at all. But just for reference, where is this coming from? Why do we have g00 equal to 0? Remember that kind of over in Fourier land, this is the equivalent condition to f being orthogonal to 1. The kind of trivial coefficient being 0 is the same condition. So over in this theorem, we have that the kind of trivial coefficient is 0, g00 is equal to 0. Anyway, just a reminder of where this comes from, so it's not totally out of the blue. We don't really need to know it for this lecture. But anyway, we want the following to hold. We kind of simplified. This was what I was calling step 1. We simplified all the way to the following. We wanted to show that the sum of GZ times G T1 inverse Z, and then we had these phases, cos of pi Z2 over N plus G of T2 inverse Z cosine of pi Z1 over N. We wanted to prove that this was less than or equal to 5 over root 2 sum of GZ squared. So this was kind of the end of where we got to last lecture. This was the end of step 1. And this is where I want to pick up from for this lecture. We'll first kind of simplify this. So we're kind of going to move in 2 steps. We're first going to simplify this to actually a simpler kind of term-by-term analysis. Then we're going to, in step 3, kind of do the term-by-term analysis. So before we move into that, any questions? People want reminders about the setup. Any questions about what I've said so far before we jump into actually finishing the proof of Gabber-Galil, which in particular just involves now proving this theorem on the bottom. Okay, if not, then let's go ahead and jump into this. So kind of what's the overall idea? Well, we still kind of have these cross terms, right? So on the left-hand side, we still basically have these cross terms that we somehow need to deal with. Oh, I dropped a 2. Sorry, there should be a 2 there. There are still these cross terms that we need to deal with. And notice that we still can't really go around kind of blindly applying Cauchy-Schwarz, because again, we'll just get 4 as our bound if we try to do this. This would basically ignore all the work we've done with these phases with the cosines. And so we have to do something a little bit more clever. We have to do something finer grained than Cauchy-Schwarz to get kind of the decorrelation to get this better bound. And how are we going to do this? Well, we're going to use kind of a classic way, a classic finer grained way of comparing cross terms to their squares, right? So we still need to somehow compare the cross terms on the left-hand side to the squared values on the right. So how are we going to do this? Well, we're going to use kind of a classic trick, which is the following claim, which is that for all alpha, beta, gamma greater than or equal to 0, and just for context, think of alpha here as maybe being g of z, think of beta as being g of T1 inverse z, and gamma as just being some parameter. And what we're going to prove is that there's a connection between 2 alpha beta and alpha squared, some version of alpha squared plus beta squared. In particular, I claim that for all such parameters, 2 alpha beta is less than or equal to gamma alpha squared plus gamma inverse beta squared. So what's the proof of this? Well, I claim it's elementary. In particular, just expand out the following relation. I think it's alpha root gamma plus beta root gamma inverse squared. So because this is a square, it's greater than or equal to 0, right? So I won't do it, but if you just expand out this square, you will exactly get this relation. So there's nothing complicated here going on. We just expand out this square. Surprisingly, by the way, this is a really useful trick. It's kind of used in a lot of places, surprisingly. So it's worth remembering this one. Okay, so I guess the issue here is this isn't quite enough for us. So I've said kind of alpha and beta you should think of as being a single value of GZ and a single value of T1 inverse Z. But we have many possible values of this pair, right? There are many possible alpha beta pairs that we're going to have to bound. And for each of them, we might want to pick a different gamma, right? There might be some, we want to pick the gamma that's optimal for that pair. If we were to just try to pick gamma equal to 1 always, for instance, this would basically just be Cauchy-Schwarz. We wouldn't be taking advantage of kind of the cosines and the decorrelation. So what we're going to do is we're basically going to define gamma as kind of a function that takes in the specific alpha beta pair that we're trying to analyze and outputs like a good version of gamma for this inequality. And I'm not going to tell you what the function is for now. I'm just going to define it as a general definition. And then later when we go into the analysis, I'm going to pick a gamma that works really well and we're going to see how this lets us get the bound. So for now, let me just maybe kind of define some notation for this type of gamma function, where we're going to be using it in combination with this claim. So define gamma is some function from Zn squared cross Zn squared. So think of this as taking maybe a pair Z and T1 inverse Z, and then outputting a gamma that'll be good for the above claim. So this maps to some kind of gamma value, r greater than or equal to 0. And just kind of for notational ease, I want the following to be true. I want that essentially gamma is anti-symmetric in the following way. For all x, y in Zn squared, I want gamma x, y times gamma y x to be equal to 1. So in other words, when I apply this claim, gamma will be gamma xy, or gamma like alpha beta, and gamma inverse will just be gamma beta alpha. It'll just be the flip. So this is purely a notational trick. This isn't really necessary, but it's very useful for the rest of the analysis. So okay, we've defined this kind of gamma. Let's now, based on this definition, let's just assume we have kind of some function that looks like this. I'm not gonna, like I said, I'm not gonna specify one yet. But let's say we have such a function. Let's kind of look at, using this claim, how can we simplify the above here? Let me maybe call this LHS for short, left-hand side. So I claim, just applying this claim to the left-hand side, we get the following. In particular, that the left-hand side is less than or equal to what? Well, we still have this sum over Z in Zn squared. And so let's look at the first term. So here we're applying we're applying the claim with x. Okay, actually, maybe let me say something a little bit more general first. So what does this claim allow us to do? If we have the term g 2gx gy, applying the claim gets that this is less than or equal to gamma xy gx squared plus gamma yx gy squared. Right, so this is basically the form of what we're going to use. Let's just plug this into this equation up here that we're trying to prove in the theorem. And the idea here is that we're trying to move from cross terms to the squares so that it looks more like the right-hand side. Anyway, so let's plug this in. So left-hand side is less than or equal to the following. Okay, so first we have this 2gz gt1 inverse z term. So the cosine term doesn't change, right? This isn't part of the inequality that we're using. So out front, we'll have maybe cosine of pi z2 over n. And then we'll have what's given by the inequality, which is gamma z t1 inverse z times gz squared plus now the flip term, right? The inverse, gamma t1 inverse z of g t1 inverse z squared. And now the second term, well, notice the second term is the same, but I've just flipped 1 and 2, right? It's exactly symmetric, but 1 and 2 are flipped. So this is just going to be the same thing, but you exchange 1 everywhere with 2. So this is now plus, okay, we have cosine of pi z1 over n, gamma of z t2 inverse z gz squared plus gamma t2 inverse z g of t2 inverse z squared. And so in particular, because the left-hand side is upper bounded by this, to prove the theorem, it's enough to show that this sum is less than or equal to 5 over root 2 sum of gz squared, right? If we can prove this inequality, then clearly we'll be done. It implies the theorem that we want to show, right? So let's just focus on proving this version. And in fact, can
I just say one thing? So just for a sanity check. So we said already that getting the number 4 there is like a trivial bound. You get to Cauchy-Schwarz, right? So just verify that if you choose gamma to be 1 everywhere, and you just say well, cosinus is at most 1, So just with the naive bound or cosinus, you get exactly the number 4, like 4 times the sum of GZ squared.
Right.
The goal here is to beat this number 4.
So if we plug in, Shahar saying if we plug in kind of a naive strategy, so one definition for gamma that would certainly work is 1 everywhere, right? Then 1 times its flip is 1 is always equal to 1. So if we plug in 1 and we bound the cosine terms, which are maximum 1, then we'll get exactly 4 of these GZ squared terms coming up each time, which is the bound we want to beat. So let me maybe just simplify this term a little bit. So everything we're in good shape now, since the left-hand side is all in terms of squares. But I want to reconfigure things a little bit so that they're all in terms of 1 parameter, right? For now we have GZ squared and GT1 inverse Z squared, but we can write this a little more simply by just collecting all the coefficients of each kind of fixed GZ squared, right? So let's just rewrite this to make things a little bit simpler. So this is equal to kind of the following. Let's fix some value of Z, and we sum over GZ squared times its coefficients. So we'll have GZ squared. And then what are its coefficients? Well, let's just take a look. So let's look at the first term. So this one's easy, right? We already have GZ squared here. So its coefficient is just this cos gamma term. So we can just write that in. So we have cosine of pi Z2 over n times gamma of Z T1 inverse Z. So that's the first coefficient we get. Now I want to look at this second term here. So here we actually, to get the GZ squared term, we have to kind of change variables. Pardon. We have to move from Z to T1Z. So in particular, what happens, I'm abusing notation a little bit, but what happens if we kind of send Z to T1Z? Like we look at T1Z in the sum. Well, this term here goes to G of Z squared, right? So we're getting kind of the correct term. And what happens to our coefficients? Well, this term goes to gamma of Z T1Z, right? So we have a gamma T1Z term. And then what happens to this cosine? So it's also multiplied by this cosine, right? And the trick now is that T1 is upper triangular, which means it fixes Z2. So when we apply T1, this term does not change at all. It still stays as cosine pi Z2 over n, because the second coordinate doesn't change at all, based on our definition of T1 and T2. So this is all just to say, what coefficient do we end up getting? Well, we still have a cos pi Z2 over n, so we can kind of factor that out. And then the other term we just get is gamma Z T1Z, just from the change of variables.
So maybe it's a good point to just pause and think, okay, so far, where have we used the structure, a specific choice of T1, T2, E1, E2? So
sure.
Here was one place, but think also before. The only thing we used before, the T1 transposes T2. That's one thing.
So we've used 2 facts in the simplification. In the Fourier analysis, we used that T1 inverse was equal to T2 to kind of simplify things in the Fourier analysis.
T1 transpose, right?
Sorry, I meant to say transpose. T1 is equal to T2 transpose. T1 inverse is equal to T2 inverse transpose. So we use this fact. Here we're using that the matrices are kind of upper and lower triangular, so that they fix, so that T1 fixes Z2 and T2 fixes Z1. But we have not yet used anything about the actual numbers in the matrices. We've only used this fact that they're transposes and that they're triangular. So far, this is all we've had to use. We'll see later in the case analysis why we picked the exact values 1, 2, 0, 1. This will be crucially important in finishing the case analysis. But until the very last step, we actually won't use these at all. We'll just use the fact that they're transposes and triangular.
Yeah, but then I don't remember who, but somebody was asking last time, like, what if we change 2 to 3 or to 5? Right? Would the proof still work? So I mean, so I forgot who asked this, but so far, everything is going to work, right?
Yeah. So I'll mention this again at the end. I was planning to talk about it, but yeah, until literally the very last thing that we do, the proof will go through with kind of any values, so long as they're triangular and transposes of each other.
Yeah. But I think in general, it's a good practice, when you read the proof or when you think, okay, what do you actually need from your assumption? Like, what is like some arbitrary choice, and what is like an important choice?
Yeah. Anyway, so let's just finish writing out this simplification. So we finished kind of the first term up here. Remember that the second term is just the same where we flipped 1 and 2. So what do we end up getting? Well, again, it's the same thing. We just end up flipping 1 and 2 here. So this is gamma z t2 inverse z plus gamma z t2z. So it's equivalent to prove that this is less than or equal to 5 over root 2 times the sum of gz squared. Okay, and so now we're clearly in better shape, right? We have sum of gz squared over here, we have sum of gz squared over here, and then there's some inner term. And what I want to claim here is that really what we want to do is actually to now ignore the outer sum. We just want to bound this inner term. We want to show that kind of for all z not equal to 0. So remember that we know that g of 0 is 0, so we don't care about the term where z is equal to 0. But otherwise, I claim that kind of this inner term is always less than or equal to 5 over root 2. And if this is true, clearly we're done, right? Because we can just pull out the maximum and we'll get the inequality that we want. Now, it might seem like maybe this is something that's too strong to hope for, that kind of every inner term is actually bounded by what we want. But I claim that it's actually, if we're going to prove the theorem kind of as I stated it, it's actually necessary that this is true. Because remember that this g here is just some arbitrary function where all we're requiring is that it's 0 at value 0. So in particular, I could take the function that's 1 at a particular value of z and 0 everywhere else. And then this bound that I'm trying to prove would exactly be that the inner term must be less than or equal to 5 root 2. So not only is it kind of sufficient to just prove this inner term, it's actually equivalent. We have to bound this each of the inner terms by, except for the 0, case where z equals 0, by 5 root 2. So let me maybe write this a little bit more formally as a lemma. And then our last step will be going into the case analysis to actually prove this lemma.
Maybe just add one thing. So maybe one way to think about this term by term thing. Remember that the function g here is really the Fourier of the original function we're trying to understand. Yeah. So this, to some extent, tells us that there are like sort of like a worst case cuts in this graph, or function test function that we want to make sure the Rayleigh quotient is large, and those that come from the characters. So if we can understand those, then we can understand everything. They are the worst case. This is one way to think about it.
So let's just restate the above. I want to prove that there exists some gamma satisfying our definition, which it maps zn squared to the non-negative reals, such that gamma of x, y, gamma of y, x is equal to 1, such that for all z equal to z1, z2, not equal to 0, 0, the following term by term inequality holds. I'll call this E of z just so I don't have to rewrite it a million times. E of z is equal to, I guess now I will rewrite it. So this is just the earlier inner term. Cos of pi z2 over n. Then these gamma terms. Plus the symmetric flip version of it, flipping 1 and 2, cosine pi z1 over n, gamma z t2 inverse z, plus gamma z t2z. We want to prove that this is less than or equal to 5 over root 2. And like I mentioned at the beginning, I'm going to cheat a little bit, and actually we're going to prove that this is less than 3.65, which will get us the 7.3 bound instead of the 5 root 2 bound. But good enough for us. The analysis will be a little bit simpler. Still proves that it's a great infinite family of strongly explicit spectral expanders.
Yeah, I mean, any constant below 4 will be fine. 3.99 will be fine.
Yeah, anything below 4 is fine. That includes 3.65. Okay, so this is kind of the end of what we called step 2 in the notes. And step 3 will be the case analysis, where we actually go in and for all values of z, we will prove this lemma. Basically, we'll define a gamma such that kind of either, we'll have two cases, which I'll explain in a second, where either kind of the cosine terms will be small or the gamma terms will be small. So kind of no matter what happens, we will win, and this will be small. But before doing that, I want to ask, are there any questions getting to this point? I guess before we jump into the case analysis and finally finish the proof of Gabber-Galil. If not, then let's go ahead and prove this lemma. So the first thing that I want to do is actually define gamma for you. So in the lemma that says there exists some gamma such that this is satisfied, let me just go ahead and kind of out front define gamma. And to do this, so define gamma. To do this, I actually need kind of two quick background things. The first is that I actually kind of want to change how I think about Z mod n. So normally, and before, we've been thinking about Z mod n as being 0 through n minus 1. But we don't have to think about it this way. We can kind of identify Z mod n instead with the interval negative n over 2 to n over 2 non-inclusive. And what am I really doing here? I'm basically just expressing the bigger numbers, the numbers that are bigger than n over 2, as kind of inverses of the smaller numbers. So group theoretically, this is exactly equivalent. And let me maybe say a little bit more specifically. So for any I greater than 0, I'm mapping I plus n over 2 to I minus n over 2. And really, this just has to do with the inverse thing that I was saying. But informally, just think of this as saying kind of, well, we're working mod n, right? Everything we're doing is kind of equivalent mod n. All the cos terms that we've set up are cyclic mod n because we're multiplying by pi. And so the fact that I'm shifting these values by n, right? All I'm doing is I'm subtracting n here. I'm moving from I plus n over 2 to I minus n over 2. All I'm doing is moving by n. And because all of our arguments are mod n, this should be exactly equivalent. It won't change anything. It's just a useful notational trick. So this is equivalent. And just helpful for definitions.
I mean, Max, also, I mean, there's another way to think about it. But if you think about the cosinus terms above, then they're like, just looking at the places where, I mean, because if the cosinus term is going to be less than 1 significantly, then you automatically have the bound that's less than 4.
Right.
So it really tells you what are the values that you want to focus on, where this cosinus becomes 1. And this cosinus is 1 exactly when z1 over n is exactly n over 2.
Right.
Which is exactly the shifting is going to move it to 0. So just be more convenient too.
Right. Yeah, sure. Yeah, I guess we're shifting to where the maximum, the worst case value is to be 0, and in the proof we'll kind of see this come out to an extent. Okay, the second thing I want to do is define a partial order on Zn squared. What is a partial order? Well, I won't define it formally here, but just think about it as an order on some kind of set where sometimes elements can't be ordered with respect to each other. So sometimes they're what are called incomparable. Let me just very quickly draw an example. So let's say we have kind of the numbers 1, 2, 3, 4, and 5, and they're ordered. 1 is less than 2, is less than 3, is less than 4, is less than 5. And then we also, over here, we have maybe some letters, like we have A, B, C, D, and these are also ordered. Like A is less than B, is less than C, is less than D. But I'm not going to require any kind of ordering between numbers and letters. So like C and 2, well, it doesn't make any sense to compare C and 2. They're different objects. They're incomparable. So this is a very simple example of what's called a partial order. And I want to define kind of a version of this for Zn squared for reasons that will become clear in just a second. So how do I want to define this? Well, I want to say that Z, some element Z is less than another element Z prime if kind of 3 conditions hold. Basically, this partial order will be kind of pointwise comparing the absolute values of the coordinates. So in particular, this holds if the absolute value of the first coordinate in Z, of Z1, is less than or equal to the absolute value of the first coordinate in Z prime. Then the same is true for the second coordinate, Z2 less than or equal to Z prime 2. And notice that this is kind of a strict relation over here. So I want them to not both be equal. I want also kind of one of these inequalities is strict. One of these is strict. So if you have z and z prime where their first and second coordinates both have the same absolute value, they do not satisfy this condition. And this will be somewhat important in the proof. They're considered incomparable. So everything else, so kind of otherwise, z and z prime. Okay, if kind of the inverse of these holds, then you say z prime is z is greater than z prime, and otherwise z and z prime are incomparable. Okay, does that definition make sense? Does anyone have questions on that definition? So we're just defining something to be less than. We're just defining an order, less than on elements in Zn squared that just looks coordinate wise. Are your absolute values smaller than the second option? That's all we're doing here. And if they're kind of not both smaller, then they're incomparable, basically. And now we'll actually use this to define gamma. So in particular, gamma on z prime will be defined as follows. It will be some number alpha greater than 1. And in particular, I'll just tell you ahead of time, we'll be setting alpha to, iPad error. We'll be setting alpha to 5/4. I'm going to use alpha throughout because it's a bit more general and I don't really want to write 5/4 all over the place. But think about alpha as some constant greater than 1. And this will be if z is greater than z prime. It'll be 1 over alpha if, on the other hand, z is less than z prime. And it'll be 1 if they're incomparable. So this covers all cases, right? If you have a pair z and z prime, either z is greater than z prime, z is less than z prime, or they're incomparable. Those are the only options in a partial order, and you always are going to satisfy uniquely one of them, at least for our definition. So first of all, maybe let's just verify that this satisfies the condition for gamma, right? We wanted gamma to satisfy that gamma xy, gamma yx was equal to 1. So what options do we have here, right? If x is greater than y, we get alpha 1 over alpha. Otherwise, if it's flipped the other way, we get 1 over alpha and alpha. And if they're incomparable, we get 1 and 1. Every time we multiply these, we get 1. So kind of based on this partial order, this gamma is indeed, does satisfy our conditions that the flip is the inverse. Okay, so the next step is actually just to go into the case analysis and to prove that using this gamma, we get the 5/√2, or in our case, 3.65 bound. So before doing that, are there any questions on the setup of defining gamma? If not, let's go ahead and move on. Okay, so we'll now actually prove the lemma, and we'll break this into two cases. So kind of cases based on, given kind of z equals z1, z2, we'll break it into cases based on the size of z1 plus z2. And it's maybe a little bit more instructive to actually draw a picture for this. So let's see if I can draw a passable picture. What we'll have is kind of a diamond, and our casework will be based upon whether z lies outside the diamond or inside the diamond. So what is this diamond standing for? Well, this is the coordinate n/2, 0. It's basically all corners of n/2, 0. So this is n/2, 0. This is 0, negative n/2. This is negative n/2, 0. And this is 0, n/2. And the cases will just be, does z lie inside or outside the diamond? So the first case we'll do is outside the diamond. And okay, mathematically, what does it mean to be outside or on the boundary of the diamond? This is just a statement about how big absolute value of z1 plus absolute value of z2 is. right? In particular, this is the case z1 plus z2 is greater than or equal to n over 2, right? So just drawing on the picture, this is kind of this scenario. Z lies outside or on the boundary of this diamond. And in fact, we'll make a bit of a simplifying assumption here. We're also going to assume kind of which quadrant Z lands in. Analyzing all of the quadrants is pretty much the same. So we're going to make our life easy, and we're going to assume that we're in kind of the upper right, the positive quadrant. So in particular, we'll assume that Z1, Z2 are greater than or equal to 0, which means we're in this quadrant here in the picture. So we're outside the diamond, inside this quadrant. That's case 2, case 1 in terms of the picture. Okay, so let's actually prove this case. So the first thing to notice kind of in this case, so I said in the beginning or earlier that we're basically going to break into two cases, one of which the gamma are small and one of which the cosines are small. This will be the case where the cosines are small. And so we're just going to start by kind of worst case bounding all of the gamma terms. The maximum that gamma can possibly be is alpha, 5/4. So we're just going to start by plugging in alpha, the worst case possible for all of the gamma terms, and just to simplify things. And let's see what this gives us. This gives us E of Z is less than or equal to 2 alpha. So we can drop the absolute values on the cosines because we're assuming we're in the positive right, the top quadrant. So they're always positive, right? Cosine of pi C1 over n plus cosine of pi Z2 over n. So this is just from plugging in alpha to all of the gammas. And then what I want you to notice is we can fix, to simplify this into kind of one. So we have two coordinates and we want to somehow show what is the maximum here. To do this, let's kind of fix one of the coordinates and examine the other. So let's fix Z1. And notice that because of, so what does this assumption imply? This tells us that Z1 plus Z2 is greater than or equal to n over 2, right? Basically just kind of being in this quadrant and in this case tells us the following about Z1 and Z2. And if we fix Z1, what does this tell us about the value of Z2? Well, this implies that Z2 has to lie in the following intervals. Z2 must lie in between n over 2 minus Z1 and n over 2, right? Because otherwise the sum won't possibly be greater than or equal to n over 2. And also by definition, Z1 can't be bigger than n over 2. So I guess this is not inclusive. So Z2 has to lie in this interval. And moreover, kind of the trick here, notice that cosine of pi Z2 over n is decreasing on this interval, strictly decreasing. Why, right? Because we're looking at this quadrant, and this is basically just looking at moving from down here, where you have cosine equals 1, up to over here where you have cosine is 0. Right, so as we increase this value inside the interval, the cosine is always decreasing. So to take the worst possible value, we can just let Z2 be equal to n over 2 minus Z1. So this simplifies our analysis a little bit. We get everything in terms of Z1, right? So, okay, a little bit more formally, what am I saying? I'm saying that we can bound E of Z by the following in terms of just Z1 instead of Z2. Cos of pi Z1 over n plus cosine of, well, what do you get by plugging in Z2 equals n over 2 minus Z1? You end up getting pi over 2 minus pi Z1 over n. But this is a term that hopefully you're familiar with, at least from like high school trigonometry or something like that, right? This is actually just equal to sine of pi Z1 over n. So in particular, what do we get? This is equal to 2 alpha of cos pi Z1 over n plus sine of pi Z1 over n. And it's not hard to figure out that cos plus sine is maximized when they're equal, which is at root 2 over 2. And so this is less than or equal to 2 root 2 alpha. And plugging in alpha, which remember we set to be 5/4, This is exactly equal to 5 over root 2. So in case 1, when we're outside the diamond and in the top quadrant, so I claim that all the other quadrants are basically an equivalent argument, we do indeed get this 5 over root 2 bound. Okay, any questions on case 1 before we move to inside the diamond, which is the second case?
Maybe just let me make just one comment here. So remember we said that if we set gamma to be 1 in the original formula, and I can go up to the original formula for the lemma. Yeah. Remember that we said that if we set gamma to be 1, then we get this trivial bound of 4. But if the cosines are not very close to maximal to 1, then automatically we get a bound that's less than 4. So really what Max showed you here is that, if we are really far away from, the case where Z1 and Z2 are 0, 0, then we can even afford choosing this bound on gamma to be somewhat slightly more than 1, and we still get a bound that's less than 4. And that's going to help us when we're trying to get a better bound than 4 when Z1 and Z2 are very close to 0. So we cannot just use the cosines as we have found in this sum.
Right. So maybe a pictorial way to view this is looking in the diamond. Right. The cases where the cosines are going to be bad is when you're kind of down here. Right. This is where both things are going to be near 1. And what we're showing is that when we're outside here, these cos terms are small enough, that we can just bound gamma by something trivial, and we'll already get the bound that we want. So maybe sorry.
Yeah, but the fact that we do have this alpha being more than 1 is going to help us next to the center. Is going to hurt us outside the diamond, but the diamond is big enough that it doesn't hurt us enough.
Right. So in fact, it's so good, that we can. So basically, these cases, remember that gamma has this inverse property, right? So when we define the biggest thing to be kind of some constant greater than 1 alpha, we're going to gain in it being 1 over alpha later on. So we're going to kind of gain this factor in the second case, where out here we could afford to lose it because the cosines were so good. The cosines were so small. But now inside, the cosines are going to be really big. So we'll actually need that alpha to be less than, or the 1 over alpha to be strictly less than 1 to get the bound that we want. Yeah, good point. Okay, so let's go ahead into case 2, and this will be the final step of Gabber-Galil. We will finally finish this. So what is case 2? We're inside the diamond. And formally, what does this mean? Just that Z1 plus Z2 is strictly less than n over 2. And we're still going to make the assumption that we're in that quadrant, that we're in the upper right quadrant. We're still going to assume Z1, Z2 are greater than or equal to 0. So just, again, to go up pictorially, we're now inside here. So this is kind of case 2. And you can already see, kind of, like we said, when you're down near this origin, the cosines are going to be really bad, right? The cosines are going to be basically 1. And what we're going to need to get the bound is that these gamma terms are actually mostly small, that they're mostly like 4/5, because remember we set alpha to be 5/4. So let's see why that's true. So first of all, let's do something similar to the last step. So last time we bounded gamma trivially. This time, let's bound the cosines trivially, because in this case, it's likely they're going to be close to 1 anyway. So kind of first, let's bound all cos terms by 1. So what does this get us? This gets us, just plugging this into the definition of E of Z, this gets us E of Z is less than or equal to the sum of 4 gamma terms. Gamma of Z T1Z, gamma of Z T2Z, gamma of Z T1 inverse Z, and gamma of Z T2 inverse Z. And now remember how we define gamma. So maybe this is a good point to bring us back to what Shahar was saying. If these terms were all 1, and we kind of chosen the trivial version of gamma, we would get 4, right? So we wouldn't get the bound that we need. So instead, we've set gamma, to be a little bit larger on the easier cases, and now we have some hope that if we can prove that some of these gammas are 4/5, then we'll get a bound strictly less than 4. And recall, how did we define gamma? Well, gamma has to do with how these right-hand terms compare to Z, right? So when is gamma small? It's small when in our partial order, T1Z is greater than Z. This was how we defined it. And finally, the way that we're going to prove this is we're finally going to use the explicit form of what T1, T2, T1 inverse, and T2 inverse are. This is literally the last possible step. We're in the last case of the last lemma of this proof, and now we're going to use the form of the matrices. And in fact, let me just let me first maybe make a lemma statement, and then I'll write out the forms of the values just so we have reference to them. But let me kind of make a claim about why this sum is going to be small. In particular, I basically claim that as long as Z1 and Z2 are not equal to 0, are not both equal to 0, we will get that kind of many of these transformed versions are bigger than Z. And that's really all we need to prove the theorem. So let me maybe state this formally before kind of moving on. Lemma, I just want to say kind of if we compare, where compare means with respect to the partial order. If we compare T1Z, T2Z, T1 inverse Z, and T2 inverse Z to Z, I claim that one of the two following cases must hold. Either, one, two of these values are greater than Z, and two are incomparable. Or two, three of them are greater than Z, and one of them is less than Z. Okay, so maybe it's a little unintuitive why this is true at the moment. We'll show it in a second. But let's just say, first of all, why does this lemma solve the problem? I mean, intuitively, all we're saying, right, is that on average, these gammas, if this is true, on average, these gammas will be less than 1, which is all we're trying to prove. In particular, just plugging this lemma into the formula, what do we have? Well, we have that E of Z is, the gammas are only dependent on, how many are greater than, less than, or incomparable. So the value is only dependent on which case you're in. And so this is less than the maximum kind of worst case possibility of which of the two cases you're in. So for the first one, what do you get? Well, by definition, we said that gamma of Z prime, if Z prime is greater than Z, it's 1 over alpha, right? So for two cases, then, we have that this is 2 over alpha. And the two incomparable ones are defined to be 1. So this is then plus 2. In the other case, similarly, we have 3 over alpha. But when you have the flip, when 1 is less than Z, it's actually defined to be alpha. And now kind of our choice of 5/4 was basically so that you get a reasonable bound on this. I claim that if you just plug in 5/4 and plug in this into a calculator, you get that this is equal to 3.65. So indeed, if you can prove this lemma, that often the kind of transformed versions of Z are bigger in our partial order than Z, then we will be done. We will have proved the full theorem, because this is kind of the last statement that we actually need to show.
Maybe one geometric way of thinking about it, if Z is very close to the center, this is going to sort of push it away from the center.
Right. So thinking about kind of this partial order, when is something bigger? It's really when it's kind of, further out from the center in this diagram. So yeah, Shahar, that's a good point. Shahar is exactly right. That basically what we're showing is these transformations are as long as Z is close to the center, are pushing them outwards and are therefore greater. Yeah, nice way of thinking of it. So I guess maybe let me pause quickly for are there any questions on this? If not, we'll go into the casework, which is actually finally the end of the theorem. Okay, if not, or at least maybe while people think of questions, let me write out what T1Z, T1 inverse Z, et cetera, are equal to, because they'll be useful references for the end of this proof. So in particular, T1Z is equal to, so this is just applying the definition of the matrices that we defined at the beginning. This is Z1 plus 2Z2, Z2. T1 inverse Z is equal to Z1 minus 2Z2, Z2. T2Z is equal to Z1, comma Z2 plus 2Z1. And T2 inverse Z is equal to, barely have room for this, Z1 and Z2 minus 2Z1. Okay, that was a mouthful. But I just want to have these written out for reference. And so now, okay, to prove this lemma, we're going to break into, so we're already doing casework, but we're now going to break into 2 more cases. In particular, for case 1, we're going to analyze where Z1 is equal to Z2 is not equal to 0. So remember that this lemma is actually for Z not equal to 0, 0. Right? We don't have to prove things for 0, 0 because G is always 0 on 0, 0, so we don't care about that, which is good because it would not work if you tried to do it for 0, 0, somewhat crucially. Okay, so we have Z1 equals Z2 and is not equal to 0. What are we going to do? Well, I claim that kind of off the bat, two of these are fairly obvious. In particular, the T1 inverse Z and the T2 inverse Z are pretty obvious to analyze. I claim that they're both incomparable. Are incomparable to Z. Why? Well, okay, so 1 and 2 are going to be symmetric here, so let's just focus on T1, T1 inverse rather. So T1 inverse has Z2 here, right, which is the same as Z. So in the second coordinate, the absolute values are obviously equivalent because they're just the same number. So what we need to prove is that Z1 minus 2Z2 is either, I guess, well, I'm saying they're incomparable. So I need to prove that it's equal to the absolute value of Z1. So to see they're incomparable, let's look at Z1 minus 2Z2. But Z1 and Z2 are equal here, right? So this is just equal to the absolute value of negative Z2. But this is equal to the absolute value of Z2. And this is because Z2 and Z1 are equal to the absolute value of Z1. So what do we get? Well, we get that the absolute value of kind of the terms of T1 inverse are exactly the same as the absolute values of Z. And we defined this to be incomparable in the beginning, right? We said that, not only do you have to be kind of less than or equal to both, but one of these inequalities has to be strict. And in this case, they're not. They're both equivalent. And so this implies, incomparable. And the exact same proof holds for T2 inverse. So I'm not going to go through it. So what's maybe kind of a slightly more complicated case, at least to me, is to prove that T1Z and T2Z are actually greater than Z. And to see why this is, again, it'll be the same for T1 and T2. So let's just look at T1 for simplicity. So again, we have the Z2 term is the same, right? So in this case, we have to prove that Z1 plus 2Z2 in absolute value is strictly greater than the absolute value of Z1. So let's write this out. Kind of what do we want to prove? We want to prove that Z1 plus 2Z2, and Z1 and Z2 are equal here, right? So this is equal to 3Z1. And we want to prove that this is strictly greater than the absolute value of Z1. And it seems like, probably this should be immediately obvious, right? I multiply something by 3, seems like it should get bigger. But I claim this isn't necessarily true unless you're kind of careful about what Z1 is. Because remember that we're working mod n. So basically, if you end up pushing Z1 too far, you can kind of wrap around and end up actually having an absolute value that's less than Z1. And in fact, here this can't happen. But I want to spend a moment explaining why. And kind of similar arguments to this can be used to prove case 2. So I'm going to go through this one carefully. And then case 2, I'm kind of just going to state and leave as a similar exercise. But let's kind of carefully see why this is actually true. So to see why, let's draw a unit circle, where over here we have, and this was actually another way to view the shifting of Z mod n from 0 to n minus 1 to negative n minus 2 to n over 2. So up here we'll have kind of equivalently negative n over 2 and n over 2. Down here we'll have 0. Here we'll have n over 4. Here we'll have negative n over 4. So this is just some representation of Z mod n. And I claim that we know that Z1 lies in this bottom right quadrant. So I claim kind of based on our assumptions, Z1 has to lie in here. Why is this true? Well, remember that we know that Z1 plus Z2 is strictly less than n over 2. And we also know that Z1 is equal to Z2, right? So if Z1 is greater than or equal to n over 4, this first equation would be violated. So we know it has to lie in this bottom right quadrant. So this is Z1. And that means that 3Z1 has to lie where? Well, it lies within these 3 quadrants. Right? In particular, we're multiplying by 3. You can only go kind of 3 times further on this circle. You cannot hit this 4th quadrant here, which is what's important. So then I claim the result basically holds fairly trivially from this. So what happens, let's say, if 3z1 kind of doesn't cross up here? So what happens if 3z1 is here? Well, then kind of 3z1 is obviously bigger than z1, right? Because we haven't circled around. So basically, this is just saying that if you're not mod n, that 3x is bigger than x, right? So that's obviously true. And what happens if 3z1 is over, once we've passed and gone over to the negative side? Well, everything on this negative side has an absolute value strictly greater than n over 4, right? Because we don't pass into this quadrant down here where the values are small. And z1, I've said, is strictly less than n over 4. So, if it hasn't passed over to the negative values, then it's kind of trivially bigger than z1. And if it has passed over the negative values, it's also trivially bigger than z1 because all of the values in that quadrant have absolute value bigger than n over 4. So in other words, what we see is that kind of no matter, based on this constraint that z1 is, between 0 and n over 4, we do indeed get this fact that 3z1 is always strictly greater than z1 by these kind of cyclical mod n arguments. Okay, so just to note, kind of what does this mean? Well, we're in case 1 up here, right? 2 are greater than z, and 2 are incomparable. I guess any questions on this case before we move to case 2? Kind of, I wanted to do this one in detail. Case 2, I'm just going to state and leave as an exercise. It's similar arguments based on the form of T1, T2, etc. Okay, if not, I'll at least state case 2. And if you want to go kind of work out this type of mod n argument for yourself, it's a worthwhile exercise, I think, if you haven't done this sort of stuff before. So what's case 2? Well, basically now we'll kind of assume without loss of generality that z1 is strictly greater than z2, and we'll still assume it's in the upper right quadrant. We'll assume these are both greater than or equal to 0. And I claim that in this case, that as I said, I'm going to leave it as an exercise, that basically T1 inverse z is less than z, but all the others are actually bigger than z. T1z, T2z, and T2 inverse z are all greater than z in the partial order. And again, this is some kind of mod n arguments using the values of these matrices, but we've already kind of seen one. I don't think it's worth going through all of them in lecture, but it's worth going through it on your own time to prove this fact. And this puts us into case 2, right? 3 of them are bigger than z, and 1 of them is less than z. And that means we have proved the lemma. And what we, the entirety of last class and most of this class was proving that this lemma is in fact sufficient to complete the proof of Gabber-Galil. So in fact, by proving this lemma, we have finished the entire proof, and we proved that the Margulis graphs are, expanding with parameter 7.3, something strictly less than 8. Yeah, so I guess there's time for a few questions. Shahar, I don't know if, I guess there's like 10 minutes to start introducing.
No, I won't. I mean, I might have something general to say, but yeah, I won't start into some zigzag today. Yeah.
Okay.
I just wanted to quickly look on this 1, 2, 3 conjecture of Lubotsky because it's related.
Yeah, that sounds good.
Yeah. So
if there are no questions, over to Shahar on that then.
Perfect. Yes. So basically, this Margulis construction is let me just connect the iPad. Give me a minute. I mean, you can ask questions. If you have any questions, Max?
I have one question. Is there any insight on how why you choose the boundary to be z1 plus z2 equals to n minus 1 over 2? Or you just try it out?
Other than this is kind of the halfway point, I don't have a great answer. I don't know, Shahar, what do you?
I think it would also work. I mean, you could choose it to be anything more than that, and it would still work. I mean, it just, the way I'm guessing it is it first came up with a proof there was these parameters, that you can play with. Alpha could be in more than one. There's this boundary, and then they just optimize the parameters so that it both looks nice and give you different parameters. Anyway, the version that Max presented is based on the survey on expanders, which is already a simplified version of the original paper by Gabber and Galil. So people have actually worked through that and simplified the presentation so that we can present this in class in 2 lectures without hopefully too many, technical details. So yeah, probably other options also going to work. I mean, the high level intuition that you want to say that maybe just connect it. I just throw something.
I do think that n over 2 is kind of a natural choice here because you're somehow balancing like the cosines being far out and then the cosines being small versus being close and then T1 and T2 being kind of expanding operators. And so kind of the natural, this as you expand out in kind of the, an absolute value in the unit circle, this is some kind of balanced quantity. And it seems relatively natural to me to pick kind of 1/2 to be the cutoff point of where you're looking.
Yeah.
Jahar's right that probably this is some optimized, set of.
Yeah. I mean, if you think about the area where we walk in is like this is where all the inputs are, right? And similarly here.
Your
this is
screen is black at the moment.
Oh, it's black. Why is it black? Oh, that's weird.
Is this just me? Do other people also see a?
Do you see black or
black screen?
I see black.
There we go.
Now,
okay.
now it's up. That was good.
Oh, but now I actually I don't see.
Now it shows the web page.
And now you have the web page for the Robotsky stuff.
So that's weird. Let me just stop sharing and try again. Oh, still not.
Yeah, still black screen.
Check something here. Okay. I don't know what's going on here, so I'll just speak without sharing anything. I'm not sure what's going on. Confused to connect. So here's one intuitive idea, the way I'm thinking about it, is that if you look at these calculations after the Fourier, then you want to make sure that the cosinus terms, the one that are next to 0, the one that you can't really control, somehow they're offsetted by something else. And something else is coming from this gamma function that is coming from the way we bound this Cauchy-Schwarz. But yeah, I'm not sure that like a super obvious like why this would be like the only choice that would work. I'm sure there are other ways of analyzing that will give you sort of some bounds less than 4. This is just the way they found, right? Nothing by any means is like the only way you could analyze this. Yeah. So maybe let's just say one thing. So the construction that we saw is an algebraic construction, right? It's a Cayley graph. Okay, it can be made into a Cayley graph or Schrei graph. So it has this algebraic nature to it. And the construction I'm going to show you next time is a very different type of construction. It's not like a recursive construction. It says if you can already construct an expander, let's say it's going to be some sparse large expander, then to do some operation on it and get a larger sparse expander. So it's going to be for very different nature. It's going to be like a recursive construction instead of like a one-shot algebraic construction. So the benefit of it is you can sort of play with how exactly you want to define expansion when you try to analyze this. I mean, we'll analyze spectral expansion, but for some applications, people analyze this for other notions of expansion, like vertical expansion. But of course, the con of it is it's harder to define. So it's this iterative process, this one-shot clean construction. But I think it's nice to know that there are different ways you can actually construct expanders, because you'll see once we move to high-dimensional expanders, that's not the case. I mean, people might discover the things in the future, but so far, as a community, we're not there yet. For high-dimensional expanders, there are very few algebraic constructions and basically no good combinatorial construction. There are some weak combinatorial constructions, but nothing that is comparable to what we know for expanders. So these are to a large extent still a wide open area. We are still looking for what could be like the analog of the zigzag construction for high dimension expanders. People have some guesses, but none of them really works well so far. And it's not clear yet if it's for like some fundamental reason or just because nobody has actually found the right way of doing it. So yeah. But yeah, I think first of all because I can't connect the iPad for some reason, and also because we'll run out of time. So maybe we can stop here and then we just start from scratch on Zigzag next lecture. If anybody has any questions. Oh, okay. So that's it. So just a reminder that the second homework is due on Monday. Okay, so bye everybody. So I'm gonna stop the recording.